Hi, and welcome to Concept Based. I'm John Hepworth, and we are doing a Year 11 advanced topic where it's a new topic. We are now starting probability and data, and we're looking specifically in the section called sets and set notation. Now, I'm going to try and cover pretty much all of the dot points in sets and set notation in this one question today. There is a fair bit of theory in probability at the start, so I'll try and cover as much of that as possible just in this one question so we can get on to the more question-based exploration of probability rather than the theory, which definitely comes later in this topic. Okay, so we've got a question here. Given the sets A, 1, 2, 3, 4, 5, and B, 1, 3, 5, 7, establish that, and there's some expression that's written here. Now, first of all, I just want to make reference to your reference sheet. So if we just have a quick look at what's on there, this is in the probability section of the advanced reference sheet. So you can see that the second expression here, probability of A union B and equals probability of A plus probability of B minus probability of A or B, is very similar to what I'm writing here. Little bit different, but very, very similar. It's the same idea. So this isn't something you'll necessarily have to remember. Like when we do this establishment, you won't have to remember the formula. But it's really good to obviously understand the concept, because this is concept based, of what's actually happening in the relationships in the sizes of sets and the size of probabilities. So that you can switch between essentially the two different types of probabilities that are being shown here, which I'll define and talk about in this video. Okay, so first things first, what's a set? So a set is just a set of elements. So we can see set A here, 1, 2, 3, 4, 5. It has unique elements in it, 1, 2, 3, 4, and 5 that are in that set. And we can use that set to do a bunch of probability calculations or a little bit of set theory. I've given a second set here, B, 1, 3, 5, and 7. I've specifically picked this second set to have some elements in it that are also in set A, so that we can look at this establish this relationship just below that. It helps by having some things that cross over. It still works. If they don't, it would just have some zeros in the equation. So what we then want to look at is some of this writing down here, some of these symbols. We've seen some of these symbols before, and some we may not have. So first of all, the symbols we may have seen before are these absolute values. I'm just going to hone in on this term right here. And we've got what looks like absolute value of A. Now, when we talk about absolute values historically, sometimes we do use them as the size of. So when we're looking for an answer and we're saying, oh, if we're looking for the length of the side of a triangle, then we might be looking at the absolute value of the answer, because a negative length doesn't actually make sense. So we'd take the absolute value. Well, that's the same sort of concept you can bring into this idea of sets, in that this absolute value symbols around the sides of the A is saying, what is the actual size of this set? And the size of the set is simply how many elements are in it. So in set A, we can see there are 1, 2, 3, 4, 5 elements, which happen to be the numbers 1, 2, 3, 4, and 5. So the size of this set is 5. It has 5 elements in it. Now, in your syllabus, there is a second notation for the same outcome that can be written. You can have small na. So the small n is saying what's the number of elements in A, and that will give you the same answer as the absolute value of A in terms of these sets. So it's just talking about the size of it. All right, now there are two other symbols in here which you may not have seen before. So there is this U symbol. I won't make it a full, I'll just make it like this. And there is this N symbol. Okay, so with these symbols, what they're actually talking about is operations in terms of sets. And the two operations that we break them down to are defined really by or and and. And I really like that the word and has an N in the middle, because it represents that N looking symbol. So this N here looks like this N here. So it reminds me that the N shape is saying and. And the U shape, therefore, is the other one, which is talking about or. So what is and or? Okay, so the idea of and is if something is in set A and in set B. So therefore and means it has to be in both sets. Where if you say, is it in set A or in set B? It could be in either. Okay, if an element is in either set, then that would be or. If an element's in both sets, then that would be and. Okay, so that's establishing what these mean. So therefore, what does this expression actually asking us to find? Well, it's really saying here that this one here, remember, is our or. That elements, the amount of elements, right? The amount of elements in A or B is equal to the amount of elements in A plus the amount of elements in B minus the amount of elements in A and B. Okay, now I don't know if me reading that through for you and replacing it with words makes it much simpler. I think we really need to go in and break down and have a look at what's going on here to try and understand this relationship. Okay, so first of all, what we might do is we might just look at the right-hand side here. Some of these parts are really easy. The first bit, it's saying, what's the size of set A? Okay, so again, we count 1, 2, 3, 4, 5. In A, there are 5 different elements. So the size of A is 5. Then it's asking us what's the size of set B. In set B, there is 1, 2, 3, 4. There are 4 elements in set B, so that is 4. Minus, now it's saying how many elements are in A and B. All right, let's go and have a look at elements that are in both A and B. So the 1 here is in both A and B. The 3 is in both A and B. And the 5 is in both A and B. Okay, so there's 3 elements that are in both A and B. So we would say minus 3. So that's that n looking end relationship that we have. So 5 plus 4 is 9, minus 3 equals 6. Okay, now let's look at the left-hand side. The left-hand side is equal to A or B. Now this means elements that could appear in either. They don't have to appear in both. So obviously 1, 2, 3, 4, 5 is in A, so we already have 5 elements. And then in B, 1, 3, 5, and 7. So when we go or, we've got the 5 elements in A, and in B, we don't need to count the 1 because we've already counted it in A. When we say it's in either, well, we've already counted it in A, so we don't need to count it. But in B, the 3 is also in A, so we don't need to count it. The 5 is also in A, so we don't need to count it. The 7 is unique. So this one here, so 1, 2, 3, 4, 5, we counted out of A. And then in B, we've already counted the 1, 3, and 5. So the 7 was unique. So that gives us 1 element in B that adds to our OR, which also equals 6, which is what is equal to the right-hand side. Now, just doing this numerically doesn't give you a full understanding of what it is. I'm doing this numerically to show you it works, so you have that sense of acceptance. Okay, numerically this works. But let's talk about why is this the case? What is it actually talking about to make all of this work for us? Well, it's saying, essentially, we can find out what's in A or B if we count all of A, and then we count all of B, essentially getting everything, including the duplicates. And then we subtract away the duplicates. Now, the duplicates occur from this A and B. So this is the duplicates that get removed. Now, we don't remove all of the duplicates. We just remove one lot of the duplicates so that we have all of the individual elements. So we counted all of A and all of B, and that meant we counted some things twice. And so we just took away those duplicates, and that will give us the A or B union that we have. So if that's a little bit confusing, maybe go back and have a look at the video where the number parts again occur and go, oh, how is that making that happen? But the idea that we're adding all of A, all of B, subtracting duplicates, and that gives us our OR understanding. Now we can use this then in the future in a range of different ways because we could be given bits of information. We could be given the size of the sets. We could be given the size of a part of, it could be the OR relationship. And from that, we could find the AND relationship across the two of them. There are a bunch of types of questions that that happens in, such as if there's two groups of people, some like basketball, some like soccer, some like both. So there's an OR, there's an AND, there's exclusive sets that are included. There's duplicates because they do both. And you can apply this formula to that situation to try and find out how many of them specifically like both or like one or the other. Or are in a certain set. So those examples will come in the future, but this is one we definitely want to establish. And just a reminder that it is on the reference sheet in this form, the probability form, not the counting form. But again, that's obviously very, very similar and something we'll look at in the future.